Let's continue in 13.1. This is on derivatives of vector valued functions. So before we get into derivatives of vector valued functions, let's take a look at real valued functions and recall how those were defined. So let's suppose this is my f of x down here. So, draw on the graph first, leave some space for taking a limit. So that's my function doing whatever, maybe a polynomial, who knows what it is. And then the definition, if you recall, for real valued functions is this. We say f prime of x is equal to the limit of f of x minus f of a all over x minus a as x approaches a. Or you can define it as the limit as h approaches 0 of f of x plus h minus f of x all over h. So both cases I'll show you here. So what you do is that's the definition of essentially the slope of the tangent line, right? So slope of the tangent line would look like, slope of the secant line. So it's the slope of the secant line, and then as you take the limit, it becomes the tangent line. So as you start approaching different values like this, you're getting these different lines. And just go down like that. Right, and then eventually, right, you're getting this one, and then those lines. And then as you get closer and closer and closer, you end up getting that tangent line, right? So it's tangent to the curve right there. So it ends up being the slope of that tangent line. So f prime is the slope of the tangent line, right? We all know that. And this is the other way of looking at it for as h approaches 0, you have basically your x plus a little bit, and then that's getting closer and closer to your value. So first you have these tangent or secant lines like that, and the slopes of those secant lines, and eventually you end up with that tangent line. So you start getting closer and closer to the actual tangent like that. And then eventually you have the tangent line as x approaches 0. So it's one of those strange results because at first you just look like it's 0 over 0. But as you know, if you look at those limits, they reduce, and they reduce to an actual number. So that's what's happening. Okay, so that's old stuff, right? That's what you would see in Calc 1. All right, so now let's define r prime of t. And it's really the same definition. It's the limit of r of t plus delta t. So that's your h part, right? Sometimes you'll see that as delta x, slight change in x. So we'll just use delta t. That's how they like to define it. Minus r of t all over delta t as delta t approaches 0. So that's the definition. I mean, you can show this in a delta epsilon way, but that's not really necessary. So r prime is that limit. So we have a nice theorem that says if r of t equals f of ti plus g of tj, and we'll just do it in 2 dimensions. If you keep going, it doesn't change at all the general case. Okay, then r prime of t is just equal to f prime of t I plus g prime of t j. So, right, you can't make the assumption based off the definition that you just take the derivatives of those two. You'd have to prove that. And we're going to. So we're going to see that little proof. So let's take a look. There's your theorem, and then we're going to prove it. So basically what I need to end up with for f prime is all of this above. I need it to look like that. And then that h above will be my delta t. And then once I have that form, that is defined to be f prime of t. Okay? So let's take a look. And you basically just expand it out and see what that looks like. Okay. So let's take a look. So we're going to now basically put in what r prime of t looks like. So r prime of t is equal to the limit, by definition, as delta t approaches 0 of r of t plus delta t minus r of t all over delta t. And then now let's substitute in my function. That would be equal to, it's going to be a long one, so it's equal to the limit as delta t approaches 0 of all this. It's f of t plus delta t I plus g of t plus delta t j minus the quantity f of ti plus g of tj all over delta t. So I'm just substituting in delta t, or I'm sorry, t plus delta t for my function, right? Here's r of t, and then, right, so instead of t, I'm putting t plus delta t and t plus delta t. So it's all I'm doing right there and there. So it's exactly this form above. And then basically all you got to do is expand it and recollect terms and distribute your limit across using limit laws, and you're all good, essentially. Okay, so I know it maybe sounds too simple, but so you get the limit as delta t approaches 0. And then, so we're going to distribute the negative across, and then we're going to put the negative with that one, and then the g with this negative delta t, and then divide the delta t by each term, and you get this. You get f of t plus delta t minus f of t all over delta ti. And then plus the limit is, you can bring, those are just terms of functions, so you can bring the limit across the sum. That's all we're doing there. And it's delta t approaches 0, and then the rest is really the same. So it's g of t plus delta t minus g of t all over delta t j. And then by definition, this, hold on a second, make that a little bigger. This, all of this, right? All of that and all of this, by definition, is what? Oh, actually, I need the limit too. So all of that is defined to be at g prime. And then all of this is defined to be f prime. Okay, so that's what we wanted to show. That's equal to f prime of t I plus g prime of t j. And so you can easily see this extends to any dimension. We're kind of sticking in 3D right now. And this is just a 2D case, but if you had another function, you just extend it out. It's no big deal. Okay, so the next thing is, and I'm not going to get into this too much right now. Maybe I'll show it to you later. But if there's my R of t, that's my function. And so you're going to have your R of t tracing this thing out like this. Okay, so that's like at the origin, that's how R of t is traced out. And then R prime of t ends up being this tangent line. So it ends up being tangent to the curve right there, like that. That's not working like it used to. Okay, so it's tangent to the curve as well. And I'm just going to kind of throw it out there right now. I'm not going to go through anything yet. Okay, so that's what you get when you do R prime. Then we'll talk more later. R double prime ends up being this vector like that. That ends up being R double prime. Okay, and then we'll define this eventually too. This is in the R prime is your velocity vector. So if you've seen any physics, that's what it's referring to. Oh, and the curve, here, let me clean this up a little bit. So we'll call R of t like that, where it's pointing up to the curve, and the curve we usually call C. So the actual, trace that the vector valued function is tracing out, that's the curve. We usually call that curve C. Okay, next, I'm not going to write these all down. You need to stop the video and write this down. I'm going to copy over all the properties, and we'll go through them. So see, that's that curve I just drew. Okay, so let's copy all these properties over like this, all of that, and we'll go through them, and then we'll prove a couple of them. Okay, let's go back, paste that in here. Okay, so you want to write these all down, and then let's talk about them. So this is properties of derivatives of R prime of t. So let's let R and U be differentiable vector valued functions of t. F is a differentiable real valued function, and C is just a real number. Okay, then this goes through all the little cases. So here's your derivative. This is using the other notation, d dt, all right? Or it's prime notation, but it's more like an operator, which works better sometimes. So if you have the derivative of a constant times R prime, just like real valued, you just factor out the constant, and it's R prime of t. Okay, and then number two is just the same as real valued. d dt R of t plus or minus u of t. You just take the derivatives of each one. So we call that linear. Basically goes across the sum. d dt of the product of a real valued function times the vector valued function. This is where you got to be careful. That's a product, not a dot product. And essentially using the product rule. Sometimes I prove the product rule. I don't know if I am today, or in my notes. So product rule, derivative of the first times the second plus the first times the derivative of the second. Because F is real valued, where R is vector valued. Then you get into the dot product, d dt of R of t dot u of t. And basically, yeah, you can do a dot product of vector valued functions, just like you would any two vectors. And again, you get the product rule, R prime of t dot u of t plus R of t dot u prime of t. And notice that when you do the dot product of those vector valued functions, you end up with a real valued function. Okay, so pause and think about that, how that works. Okay, you have vector values, doing whatever. When you do the dot product, you get a real valued function, like f of something, g of t. It's not a vector valued function anymore. And then same sort of thing here for the cross product. You do the r of t cross u prime of t, etc. So you do that, and that is still a vector valued function. 6 is chain rule, right? R prime of t, r prime of f of t, sorry, is r prime of f of t, and then times f prime of t. And then 7 is just a constant, so derivative of a constant 0. Okay, so the next one is a theorem we will be using. So let's take a look at that. Yeah, that's right. So this is a theorem, and we'll prove this theorem. So it's related to the above. That it uses those properties, but I'm not going to go through those proofs. I'm sorry, we're going to go through those proofs, but we're going to use those properties of that theorem to do this theorem. So this is one that we use a little bit later for a few things. So let r of t be vector valued, right, as defined above, and we're going to say the magnitude of magnitude of r of t is constant. Okay, so, or we say it's constant. So where we're heading to this is, suppose you basically take r of t and then you divide by its magnitude. Well, if you do that, then it's always length 1, and we'll get into that later, but then it is a constant magnitude. It doesn't have to be 1, but this theorem says it's a constant. Okay, so that's your hypothesis. So if that's true, then r of t and r prime of t are orthogonal, right? Or if it's in 3 dimensions or 2 dimensions, we say they're perpendicular. So orthogonal actually is defined to be dot product 0. So that's essentially what we have to prove, is to show that the dot product is 0. So let's look at the proof of that. All right, so first what you do, consider r of t dot r of t. So you're doing a dot product with itself. Now, going back to vectors, what do you get? So if you do so picture like b dot v, what does that equal to? So r of t dot r of t is a dot product with itself. That equals, do you remember? That's the magnitude of the vector squared. Okay, and we know that's a constant, or it's in the reals. It's just a constant number when you get the magnitude squared is equal to a constant. Okay, so a constant. So we then have r of t dot r of t equal to a constant. Now, differentiate both sides. So if you differentiate both sides, we're going to the right-hand side 0. Left-hand side, we got to apply which property? So left-hand side, we're going to apply this property, right? That's what we're going to do. But it's the same value. Okay, it's r. All right, so when you do that, you get r prime of t dot r of t plus r of t dot r prime of t equal to 0. And then you simplify that a bit, combine, right? It's the same term. You have commutative property for dot product, same term, so therefore it's just 2 times r prime of t dot r of t equal to 0, or that's divide by 2 and you get r prime of t dot r of t equal to 0. And by definition, therefore, r and r prime are orthogonal. All right, so we're going to use that. That's going to be an important idea we will see in a bit, and what the geometry looks like of r and r prime when you have certain conditions. Okay, we'll be defining a few things. Okay, so the next thing is really just defining this to be a particle. So this is on motion of a particle. So you don't have to think of it as a particle. I mean, r prime of t could be kind of anything that has a vector valued, way of looking at it. But we often think of that particle being positioned by r of t. So the particle is the x, y, z in space. And so if we think of r of t, we call that a position vector. So r of t is called a position vector function. Then and this is where I'm going to just kind of roll along here, r prime is equal to v of t is the velocity, and then r double prime of t is v prime of t is the acceleration, is a of t, or acceleration. Okay, and then if you take the magnitude of r prime of t, which is the magnitude of v of t, that's considered the speed. So let's just look at a simple example here, and that'll wrap up 13.1. All right, so, and again, I didn't, get into all the background of why this works. Sometimes we just got to roll along with it. So check out some of the book concepts online. Just, type in position of particle, r prime or r, velocity, that kind of stuff. A lot of stuff will come up on that concept. So here's an example. So let's let r of t equal t squared plus t I plus t cubed j. So we'll stay in 2D, and then t is 0 to 2. Okay, so I actually usually have everybody do this in class. So find v of t and a of t. So what I'll do this time, I'll just tell you what to do. You try it, and then I'll just paste it in. Save a little time here. And then B, and I'll give you a couple of hints of how to do it. Sketch it. This is like when you first start any sort of sketching. You'll just plug in points. So sketch V of 1 and A of 1, and then you want to put your initial point at whatever x is. So you want to move your vector to wherever the initial point is. Okay, so it's A is pretty easy. A and B are pretty easy. I'm sorry. Finding V and finding A is pretty easy. You just do the derivatives. Okay, and then you want to look at it like this. And actually, I'll let you work on it. So try it. Okay, so try that. And then I'm going to come back. I'm going to go ahead and paste in the result. Okay, so I like to do it like this. Okay, so try it. Pause. And now you can see what it is. It's right here. But we'll paste that in so we have a full set of notes. Let's see. Here's A. All right, so that gives you everything there. There we go. All right, so let's go over this a little bit. So here's your r prime. So there's your velocity vector. V prime is your acceleration vector. And then when you do V of 1, you get 3, 3, and 2, 6. So what I was referring to is how to sketch it. And so when you're sketching this, really what we can do is just plot points. So I wrote out r. So here's t squared plus t and then t cubed. And then your t values are going from 0 to 2. So here's 0, 0.51, 1.52. And you plot the points. You get so here's your 0, 0. So you start at 0, 0. And then when t is 0.5, you evaluate to get your x and y. So you get 0.75 and 0.125. So it's really shallow right there. And then you get this point here, 2, 1. Right? And then it starts to grow. So you get this basic curve. It's basically a polynomial is what it is. All the way up to 6, 8. So here's 6, and the way up here is 8. And then the part that I wanted to be more clear on is when you plot V of 1, what I wanted you to do is actually count out V of 1, but start at 1, which is basically 2, 1. So you start here, and then you count 3, 3. 1, 2, 3. 1, 2, 3, and then there's your vector. And see how that is exactly tangent that I just talked about up there? Okay, so this is just just want to do one example where you see that it's actually tangent. And then when you plot the acceleration, again, you start at 2, 1 here, and then you count out 2, 6. 1, 2, and then 1, 2, 3, 4, 5, 6, and then you get this as your acceleration vector. Okay. Now, if we'll get into that. I was going to talk about the theorem above. So one thing to note is the acceleration vector always points on the inside of the concavity. I don't think I get into the proof of that, but that's just geometrically what's going on. All right, so 13.2 is next, talking about integration, and then we get into defining more stuff. That'll take a while. Okay. That's it for this section.